The spectroscopy of aldehydes and ketones is very interesting. There are methods of spectroscopy are really very well geared towards identifying carbonyl compounds. So look in our chapter 12 notes for the discussion of carbonyl IR absorption. So it's the very last page of our IR discussion before. Please memorize this number. 1715 is the standard ketone carbonyl frequency in IR. So that frequency is increased if it is an aldehyde. It is decreased if the carbonyl is conjugated. So if you've got 1730 or something, that's most likely an aldehyde. It could be other things, but from what we've talked about, aldehyde sounds good. If it is conjugated, it'll be lower. If it is a conjugated aldehyde, it could be around 1715 because those are opposite factors. One interesting new thing for us to look at is that aldehydes show a CH stretch with two interesting peaks at 27 and 2800. So there are two different types of stretching frequencies that can happen with an aldehyde CH. So if you see those two peaks at 27 and 28, that's very diagnostic of an aldehyde. So this compound has all kinds of interesting things. It's got the carbonyl showing, it's got the little bumps there for the benzene ring that we like to talk about. It's got the two peaks, 27 and 28 for that aldehyde. So this is obviously some sort of aromatic aldehyde, like benzaldehyde, which is shown there. If I have an NMR spectrum, we also have something very characteristic. The CHO hydrogen, right, the hydrogen attached to the carbonyl is shifted way downfield, right around 10 ppm. And that's about the only other thing that shows up that far down. All the aromatic resonances don't get much above 8. So if you've got something between 9 and 10, that's an aldehyde hydrogen, right? Almost certainly. So this compound has a quartet as the aldehyde hydrogen, which means there's 3 hydrogens adjacent to it. So over here, here's a doublet, which means there's just 1 hydrogen next to it. So the methyl group is a doublet. The aldehyde hydrogen is a quartet. So that's a doublet and a quartet is a characteristic CH3, CH pattern. Mass spectroscopy of aldehydes and ketones. Look back in our MS chapter, review the McLafferty rearrangement. By now, I would like you to be able to draw the mechanism for the McLafferty rearrangement. It's pericyclic, so sort of looks like the Diels-Alder again. Start with the carbonyl attacking a gamma hydrogen. Here's our nomenclature again. Alpha is next to the carbonyl, then beta, then gamma. So do 3 carbons away from the carbonyl, an H on that. So start with the carbonyl attacking that H, CH bond breaking, making a double bond between gamma and beta, and then beta and alpha breaking, making a double bond between the carbonyl and alpha. So that ends up splitting between alpha and beta and splitting between the gamma carbon and its hydrogen. So it ejects a neutral alkene and leaves us with a radical cation that used to be part of the carbonyl that still contains the alpha carbon and still contains whatever was on the other side of the carbonyl. So it's like a cleavage between alpha and beta. Now, alpha cleavage itself, where we break the CC bond attached to the carbonyl, so that breaks the carbon alpha bond. That's much simpler. It just makes a resonance stabilized carbocation. Okay? There's no carbocation. There's a radical cation up here because we ejected a neutral ion here. With alpha cleavage, we eject a radical, which we don't see, and then we're left with the carbonyl carbon and whatever was attached to it on the other side. So take a look at this mass spectrum here. I bet we can analyze this. What's this look like? 100. It's not halfway. That looks like 114 to me. Okay, that's the molecular ion. That's the whole molecule. The base peak is 43. 58 is also important. Okay, those are the marked ones. So 114. Let's do some fast math in our head. 114 minus 58. Here's my calculator here. That's minus 56. 114 minus 43. That's minus 71. Okay. 58 from 43. That's a difference of what, 10, 15. Okay, so that could be a minus CH3, right, if we see that. Although in carbonyl compounds, like we have here, we have these two different fragmentation modes. One doesn't make the other, but at least this tells us what they're different by. So, gosh, what do we got here? We lost 56 to get 58. We lost 71 to get 43. What kind of carbonyl compound makes 43? Here, C double bond O, right? That's 12 and 16, that's 28. If I add 15 to that, 28 and 15 is 43. So that looks good. This looks like it came from alpha cleavage. So base peak came from alpha cleavage. So we know we have a methyl ketone. One methyl ketone up to 114.43. I need 71 to get up to 114. How many carbons can I add? I can do 5 carbons, right? 6 times 12 will be 72. So 5 times 12 is 60, right? That's 5 carbons and 11 hydrogens. That makes sense. That's a alkyl chain. So what happens if we just did C double bond O, CH3, and then 5 more carbons, 5 carbon chain, right? 1, 2, 3, 4, 5, CH3. 1, 2, 3, 4, 5, 6, 7 carbon. So let's see if C7H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 O adds up to 114. I bet it does. Yes. So we don't know about the we don't know about the branching on the side. That could be some variation of it. But the thing is, this is long enough to do a McLafferty rearrangement. So let's see if that gives us our 58. It has to if they highlighted it here, right? So if I redraw my carbonyl, put alpha down, CH2, okay, put beta up, put gamma with 1 hydrogen over there, and then everything else beyond that. All right, here's our gamma. Oops, made alpha. Gamma is like that. Here's beta, here's alpha. Start with the carbonyl, getting the H, break the CH bond to make a double bond, break the alpha beta bond. What we end up with is COH, CH3, double bond, CH2, radical cation, plus whatever else we ejected, right? Double bond, then CH2, CH3. So is that 58? C3, 12, 24, 36, and 16 is 52, 3, 4, 5, 6, 7, 8. There's our 58. So base peak came from alpha cleavage. The other peak labeled here came from McLafferty. Molecular ion is just a ketone. Again, there could be other branching that could happen here on the gamma. We could have another methyl group on the gamma or something like that. But this is a compound that's consistent with that mass spectrum. I like it. 1, 2, 3, 4, 5, 6, 7, 2-heptanone. So Here I've got just some NMR spectra for you to practice with. I invite you to stop the recording and see how far you can get on these. These are kind of challenging. The ones on the exam will probably be a little simpler than this, but these ones will be good practice.